Okay, question 15. If the tyres of the car provided a total maximum amount of grip of 20,000 newtons, what is the maximum speed the car can travel at and still successfully complete the corner? Okay, we're given the radius from the previous question, and that was 25 metres. And we were given the mass of 1,200 kilograms. Whoops, 1,200 kilograms also. So use F equals mv squared over r. So the previous question we used acceleration equals v squared over r. And as we know that F equals ma, mass times acceleration, well, this is equal to acceleration when talking about circular motion. So force is just mv squared over r. Okay, so that's really just the same formula with this integrated into it. So mass is 1,200 kilograms, and that's why they don't give you all of these, every single formula in the formula sheet, because you're really expected to know the relationship between these two formulas. But anyway, you've got your cheat sheet, and if you don't know that relationship, you can pop it on your cheat sheet. So was it 12,000 kilos? 1,200 kilos times by v squared. That's the maximum speed we can go around this corner when we have 20 kilonewtons of grip available to us, and the radius is 25. 20,000 times by 25 is 500. 1,000 equals 1,200 v squared. Divide both sides by 1,200, and then square root both sides, and we have v equals 20.4 meters per second. Question 16, okay, no more errors. This says bike. Draw an arrow or arrows indicating the direction of the net force acting on the bike. And you ride a bike, you don't drive a bike. Label the arrows. Okay, so the arrow should be pointing towards the centre of the circle. And you can do centripetal like that. F subscript C, or you could write centripetal force, whatever you like. Following question, okay, now we're getting on to our orbits. And this one, what's the speed of the Hubble Space Telescope? Okay, speed, orbital radius. So what we're going to use is we'll use 2 pi r over period. And all this is alright, this is the distance around the outside of a circle. So if this is r, this distance around there is equal to 2 pi r. And the period is the time it takes to go all the way around, so that's distance, and the period is the time. So there's really nothing terribly fancy about this equation. So v equals 2 pi times by 7 times 10 to the 6, so 6, divided by the period, which is 5820, and that comes to 7,557 meters per second. Okay. 18. What's the size of the gravitational field strength at a distance of that from the centre of the Earth? Include a unit in your answer. Gravitational field strength is G equals Gm over r squared. So G equals universal gravitational constant is 6.67 times 10 to the minus 11 times by the mass of the Earth, which is given to you on the formula sheet, and is where is it? I think it's 5.9. Oh, it's 5.98 times 10 to the 24 divided by r squared, which is given to us as 7 times by 10 to the 6, and we work all that out, and we get G equals 8.2 meters per second squared. Now, this is less than what we know the exact gravitational field strength of the Earth's surface to be, which is this. But that's right, because what are we, 1 million metres away from the surface of the Earth. I think the radius of the Earth is about 6 times 10 to the 6, I think, can't remember. So it should be a bit less. We know that the gravitational field strength decreases as you go away from the mass. Okay, question 19, using the data supplied, calculate the mass of the Earth. Okay, so we're actually, for this, we're using the same equation, mass of the Earth, r squared, so, mass. So we use G equals 10. We know it's 9.8, but in these exams we're using 10. 6.67 times 10 to the minus 11 times by capital M divided by r squared. Now the radius of the Earth, I am going to need it now. Oh, I found it. 6.37 times 10 to the 6. 6.37 times 10 to the 6. So we times both sides by 6.37. That's got to be squared. Ooh, almost made the mistake there. 10 equals 6.67 times 10 to the minus 11 times by m divided by square of 6.37, which is 4.06 times 10 to the 13. Multiply both sides by 4.06 times 10 to the 13 gives us 4.06 times 10 to the 14 divided equals 6.67 times 10 to the minus 11. M divide both sides by 6.67 times 10 to the minus 11. 6.67 times 10 to the minus 11, and that gives you a very large mass of 6.09 times 10 to the 24 kilograms. When we know from our sheet with all our information on it that the mass of the Earth is 5.98 times 10 to the 24 kilograms, which is obviously quite comparable, especially considering we've used a really round number here. Okay, last question. All right, then move so Okay, the further away something is, the slower it moves. Okay, as the gravitational field strength decreases, it moves slower through its orbit. Now, the value of r cubed over t squared. So this is another good formula to have. R cubed over t squared is equal to, oh my gosh, I think I've forgotten G. Oh, I don't want to write it because I think I'm... Anyway, the formula that's got this on one side and GMM over r squared, something, anyway, on the other side, is very handy to know. And don't forget that this ratio is fixed for every single thing that orbits the same central body. So in this case, we're talking about the Earth here and the Moon here. So if we move this further, closer in or further out, it's still going to have to conform to the same ratio here. So whatever r cubed divided by the square of the period is going to fit for every single thing orbiting the Earth. So if you've got a satellite that's very close to Earth, whereas the Moon's farther away, this radius has decreased a lot, its period just decreases a lot. All right, it takes 30 days for the Moon to go around the Earth. Some of these satellites take 90 minutes. So the value of r cubed over t squared is the same for all satellites orbiting.
What are you doing?
Recording a podcast. Do you want to appear on it?
What? A reporting podcast?
No, I'm recording a podcast for my physics students that you've now just barged into. Don't eat my lunch. Don't eat my lunch.
What is this? Dumpling soup.
Yep. Therefore, if the radius... Homemade dumpling soup.
Dumplings homemade as well?
Yep. No, I didn't. In case you're wondering if I made them.
They look delicious. They're not very neat though.
I'll report back to Tanya. She'll be devastated to hear. Jeez, it's so hard to write with this thing. It's so messy. All right, I hope that answers the question. If not, come and see me tomorrow. I'm done.